Welcome to part 2 of the factorising and solving cubic or polynomial functions. So this time what we'll look at is the addition and subtraction of perfect cubes, what they call rational root theorem, and finally finish on a VCAR problem. So let's get on to addition and subtraction of perfect cubes. So basically there's two identities that you can memorize. So if you've got the subtraction of perfect cubes in this form, then this is what the factorized version of it's going to look like. If you've got it in this form, like you've got the addition of perfect cubes, then this is what it's going to look like. So your choice here is to memorize this, or you can use equating coefficients. So let's have a look at this, factorize it and solve it. Now, first thing to note is this is just the standard cubic move down 27 units. So negative 27, and it's going to look like that. Okay, so when we solve it, we're going to get one x-intercept only. All right, so the first thing is that we'll go p of, and what we'll do is try something. So it's going to be p of 3, because 3 cubed is 27. 27 take away 27 is 0. So p of 3 equals 0. Therefore, x take 3 is a factor. And basically, we already know that this solution then is going to occur at x equals 3. And we could think about that also by solving when x is equal to 0. But we want to factorize it first. All right, so let's rewrite it. P of x equals x take 3. Now, this one, it's going to be x squared plus bx. And this is going to be plus 9, I think. Yeah, so negative times a positive is a negative. 3 times 9 is 27. Right, so what's b going to be? So it's going to be negative 3b, so that multiplied by that, and plus 9, so only the coefficients, we're not worried about the x's, equals, now what's the x term in this? It's going to be 0x. Okay, so I can rewrite it as x cubed plus 0x squared plus 0x, take away 27. So it's going to be 0. That means b is going to be equal to 3. So the factorized version is p of x equals x take 3 x squared plus 3x plus 9. Let's let it equal 0. So 0 equals p of x. X equals 3. X squared plus 3x plus 9 is never equal to 0. As discriminant is less than 0. Alright, so what I've said is it's got one solution at x equals 3. The other one can't be solved, so this part of it can't be solved via the null factor law because it's the discriminant is less than 0. Now, how did I know that? Well, I know it for sure because if you consider the original graph, x cubed take away 27, you just know basically that it's going to have only one x-intercept, so this other one can't be solved. So I'm just assuming that the discriminant is less than 0, but if you run it, it will be. Alright, here is the next one, and you can pair this up with the identity as well. So this is this identity here, so it's got x take away a, I don't even know how to use the identity, so I just use equating coefficients. Alright, p of x, okay, so p of negative 5 equals 0, so negative 5 cubed is going to be negative 125, plus 125 is equal to 0, so therefore x plus 5 is a factor. Alrighty, so what we're going to do is rewrite p of x as x plus 5, x squared, and this is going to be plus bx plus 25. 5 times 25 is 125. Alright, now remultiply. We've got 5b, that multiplied by that, plus 25 equals, again, 0, because the coefficient of the x term is 0. That means b is equal to negative 5. So p of x is equal to x plus 5, x squared, take away 5x plus 25. 0 equals p of x, or p of x equals 0, x equals negative 5, and x squared take away 5x plus 25 can't equal to 0 as discriminant is less than 0. Okay, and so again, how did I know that? Well, x cubed take away 125 is just a standard inflected cubic like that. Okay, so I know that the only solution is going to be that one. Alrighty, given that p of x is this, and a factor of p of x is this, alright, so that means that, so if this is a factor, then p of -1 equals 0, and p of 3, because if it is a factor, then it has 0 remainder when I pop -1 into this, and when I pop 3 in, the remainder, according to the remainder theorem, is 24. Okay, so let's do it. 0 equals, now I'm going to put -1 in, which gives me -1 plus a take m take away 6. So there's my first equation. Let's tidy that up a bit. I'm going to add 1 and add 6. So that's going to be 7 equals a take m. Alright, now 24 equals 3. 27 plus, what's that? 9a plus 3m take away 6. Right, add 6 is 30, remove 27 is 3, 9a plus 3m. So we'll call that equation 2. Equation 1, what I'll do with equation 1 is multiply it by 3 to eliminate the m. So I'm going to go 21, so this times 3 will be 21 equals 3a take away 3m. Alright, now what I'll do is add them. So the m gets eliminated, and we've got 12a equals 24, a equals 2. Okay, so there's our first solution, a equals 2. Then we just pop it into equation 1 or equation 2, doesn't really matter. 7 equals 2, take away m, so I'm just popping it into equation 1. What's that? 5 equals -m, m equals -5. Determine the values of a and m. Sure, it's those two. Alright, the rational root theorem. Okay, so consider this. Define the function on your calculator or Mathematica and try to find an integer solution. Okay, so what we've been doing on Mathematica is, let's clear f first of all. And let's define it. So f(x) blank is 2x cubed, take away x squared, take away x, take away 3. Alright, so we've got really 3 choices. So we've got f of 1. Alright, let's just put down our choices. So we've got f or p of 1, p of -1. This is according to this being -3, and p of 3 and p of -3. Alright, so let's just try them. So f of 1, let's do f of -1, no, f of 3, no, and f of -3, no. Okay, so all of them are not equal to 0, which means that none of these, x plus 1, x take 1, x plus 3, x take 3, are linear factors. So it says here, this polynomial does not have an integer solution, but could have a fraction for a solution. So when factorized, this will look as follows. So we're going to have linear, followed by quadratic. And what we'll note here is that rational root theorem comes up when we've got a coefficient of the cube term other than 1. Okay, so what we'll note is that this term here can look as follows. So p of x could be equal to, so we could have 2x, which means that this will be x squared, and this one here could be plus 1, which means this one here will be -3. So I note here that that will give me what I need there, and that 1 times -3 will be -3. So this is a possible option for this first bracket here. Now we can have other versions of this. We could have 2x take 1, which will be x squared, and then that one will be a plus 3. We could have 2x, and this could be plus 3. That would be then take 1. And the final one that we can have is 2x take 3, x squared take 1. All right. So what that means is that each of these could be a linear factor. So these could be linear factors. So we've got to test them using the remainder theorem. So what we would have to do then is do p of, this one here will be negative a half. This one here will be p of a half. This one here will be p of negative 3 on 2. This one here will be p of 3 on 2. And what we're interested in is which one of them gives us 0 remainder. Okay, so negative a half. Now, in theory, I should be doing this by hand, but I'm not, because it's a lot of work, a lot of putting numbers in. So I encourage you to use your calculator on this. So negative 3 on 2 is not right. So last one, there's the winner. So p of 3 on 2 equals 0. That's not equal to 0. That's not equal to 0. Not equal to 0. So therefore, this one here, the very final one, 2x take 3, is a linear factor. All right, and then once you've got your linear factor, you can equate coefficients and factorize as normal. So the idea is that even if you have tried to do p of 1, p of negative 1, p of 3, p of negative 3, it still may factorize, but you may have to build up that factor or get that linear factor by trying p of a fraction. All right, so let's try this one now. So I can see here, the skill will be to kind of know what to do or what to put into your calculator. So we've got p of x could be, and we've got bracket, 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 bracket. So I know that it's not going to be 1, negative 1, 5, negative 5. So I'm going to try 3x, which means that that is x squared. And I'm going to try 1, which means that's negative 5. So that's one possible option. We could get take 1, which means that's x squared plus 5. We could get plus 5, which means x squared and plus 1. 3x take 5, x squared, and that's take 1. And we've exhausted all the options. Now this is again assuming that p of 1 is not equal to 0, p of negative 1 is not equal to 0, p of 5 is not equal to 0, and p of negative 5 is not equal to 0. So I've tried them and found that I can't factorize this thing. So I need to kind of use this idea of the rational root theorem. All right, so what we'll do is we'll attempt to factorize first of all by trying p of negative a third, p of a third, p of 5 on 3, 5 on 3 equals, 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 and equals. Okay, so again, what I recommend you do, you don't want to bother doing that on the calculator, or by hand. So I'm going to go over to the calculator. Fx, I'm still a little slow on Mathematica, so excuse the speed. X squared plus 2x take 5. Okay, f of negative 1/3. Come on, let's get it quickly. F of negative 1/3 is f of negative 1/3. Let's try again. Okay, something weird's going on. Okay, so did you see my mistake? It is the blank that I forgot. Now again, I do know what I'm doing, I promise, but I've got years of indoctrination of using class pads and TIs. So yeah, all right, here we go, we're in business now. So here's negative 1/3, no. 1/3, no. negative 5 on 3. Bingo. Okay, so we're going to say not equal to 0, equal to 0, not equal to 0, and not equal to 0. Therefore, x, which one is it? 3x plus 5 is a factor. Right, so now we can write p of x equals 3x plus 5, x squared, what is it? Plus 1. Should we take 1? So positive 5 times negative 1 is negative 5, so that should be positive. Okay. Plus bx. Okay, so looking at the coefficient of x, it's 2. Now I'm just going to multiply, so what's it going to be? It's going to be 3x times negative 1, so that's negative 3, and 5 times bx plus 5b equals 2. That means 5b equals 5b equals 1. So p of x, when factorised, is going to be 3x plus 5, x squared plus x, take 1. So yeah, there it is. Can that be factorised more? Doubt it. No, that's it. Let's just try that. So factor f of x, not with the blank. Yeah, there it is there. Okay, so there's the factorised form of it. Hardly ever comes up in an exam, or I haven't seen it anyway, because why? It's just too much work in exam 1, and if it's exam 2, why would you be doing all of this work when you can just use factor in exam 2 and it produces it? Okay, so exam 1, no way they're going to get you to do this amount of work, and exam 2, what's the point when you can just use factor? Right. Okay, so this last problem is from exam 2 VCAR 2014, and you can see here the state drops away considerably in this one here. It's probably a fairly early problem, maybe even question 1. Right, so we've got f of x being this function here, looks like a quartic. G of x is also a quartic. Express g of x in this form. So x is going to come out as a common factor. So we'll go g of x equals x, x to the 3 take 8. Now I need to factorise that. Now I could use the identity or the equating coefficients method, but with the calculator handy, I'm just going to go for it. So I'm going to say, can you factor x cubed take 8, please? And it's going to be x take 2, x squared plus 2x plus 4. Not quite in the required form. That's right. That needs to be in turning point form. So x squared plus 2x, halve this, square it and add it, subtract it, and add the 4. So I've just completed the square, which means that that becomes x plus 1 all squared plus 3. So x take 2, x plus 1 all squared plus 3. And now it looks like it's in the required form. Okay, so now describe a translation that maps the graph of f of x, which is this one here, to the graph of g of x, which is this one here, or this one here, as we just found out. Now, what are we going to do? Are we going to map that to that, or that to that? Well, the reason question A exists is a big hint. Okay, so they're telling us use this. Otherwise, why would they get you to do it? Why would they get you to write that in that form there? So let's have a look at how f of x was changed, like what was done to this to get it to look like this. And you can see here that this was moved 1 unit to the right. Okay, so x take 1, 1 unit to the left, okay, to become this x. This one here was at positive 3, okay, and we wanted it positive 2, so it's moved 1 unit to the left. And this one moved 1 unit to the left would involve us just popping x plus 1 into the function. So this is a translation 1 unit left. Okay. Find the values of d such that the graph of y equals f of x plus d has one positive x-axis intercept. Okay, well, it's probably worth just having a think about the graph of this. So let's think about what g of x, no, it's not g of x anyway, it's f of x, what this graph looks like. All right, so what we'll do is we'll go ahead and run a plot on Mathematica. So plot x take 3. Actually, let's define it as a function first. So we'll go clear f, then we'll go f x equals x take 3, x take 1, x squared plus 3. Alrighty, now what we'll do is plot it. So plot f of x for me, where x, let's say, just looking at the values there, if I imagine solving that via the null factor law, I'm just going to go -5 to 5. And what I'll also do at the same time is restrict the range. So I'll use the plot range command and say, I don't know, between -2 and 2. All right, let's just see what comes up. All right, so not a lot. So it's going to kind of go back down there. So just change the this. Let's go further than that. So -10 maybe to 10. Let's see if we can get a better look at it. Okay. Alright, so it's got the 2x intercepts there, obviously, which is the 3 and the 1. Okay, yeah, that's actually got exactly what it needs. Okay, so find the values of d. So what they're doing is they're doing a horizontal translation by a factor d, and they want us to tell us, or want us to tell them when it's going to have one positive x-axis intercept. Alright, so this is where Mathematica really comes in strong. So we're going to go manipulate f of x plus d. Let's do the manipulate the plot of f of x plus d. Now, x is between, let's go the original -5 to 5, with a plot range between -2 and 2. And our d values, I don't know, let's just start with between -5 and 5. Alright, so let's just see what this does. Alright, so we've got f of x plus d. Alright, so here it is. So what you can see here is that as I'm moving this slider d, it's changing the position of those x-axis intercepts. Let's click the plus here and look at what the d value is. You can put a third parameter in here, which is 1. That changes the increment to 1. Alright, so I'm just going to change that now. 4, 3, 2, 1, 0, 1. Alright, so let's just see what matches what we're after. So find the values of d such that the graph of f of x plus d has one positive x-axis intercept. So here is where it has one positive x-axis intercept, is when d is an element. So 1 is one of the values, and as I increase, what's going to happen is, so it's gone from, so it's between 1 and 3. Now 3 we're going to exclude, because 3 means that this x-intercept is on 0, which means that it doesn't count. So we're going to exclude that. But I think we're going to include 1. Yeah, we are, because this is one positive x-axis intercept. So we're allowed to include the 1 there. And let's just bump it down to 0 just to confirm. Now we've got 2 positive x-axis intercepts. So D is an element between 1 and 3, include 1, exclude 3 itself. Alright, what about 2 positive x-axis intercepts? So let's slide that back to where the tipping point was. So we're going to say D is an element. So currently it doesn't have 2 positive x-axis intercepts, it has 1. But we're going to start with 1. So any value not including 1 itself but larger than it, so 2. No, it's actually the other way around. It is negative infinity. So where's my rubber? There. So we're going to start at negative infinity. And we're going to go all the way up to 1, but not 1 itself. Okay, so there's like negative 2, negative 3. We've still got 2 positive x-axis intercepts, although it's off the graph at the moment. But goes down to down to 1, and we just get the single positive x-intercept. So yeah, D is an element between negative infinity to 1. Alright, and I think that means that I think I set up to 11 or 13 or whatever I didn't set last time. Just do the rest of those questions. Alright, good luck.